Good morning, everybody, and welcome to this Sigma-HSE webinar with the title of Challenging Assumptions Around Dust Combustibility. Hopefully you can all hear me and you can see my slides. So Sigma-HSE holds these webinars monthly on different topics that we think are of interest to the industry. So welcome if you're new to this. And welcome again for those who commonly join us on these webinars. So as I said, today, challenging assumptions around dust combustibility. So just a little bit in way of introduction to myself and the company, first of all. So my name's Andrew Fowler. I'm currently the Technical and Operations Director here at Sigma-HSE over in the UK, based in Winchester, down on the south of the country. And there you'll see my experience. So I'm getting on a bit in years now. So I'm getting close to 40 years experience in this subject of process safety. And you can see that I've had experience in major hazard industries, in chemical manufacturing, which is my background. Also 17 years as a process safety specialist inspector and risk assessor within the UK's Health and Safety Executive. So I should know a little bit about this topic by now. And process safety being around, in this context, preventing fires and explosions. Sigma-HSE is a global process safety consultancy, and we also have the luxury of laboratories for testing the properties of materials and substances, which is part of what I'll be talking about today primarily. Okay, so we can test the properties and we can make sure that those materials can be handled safely within your processes according to the legislation and so on and so forth that's pertinent. So we are a global company. We have headquarters over in Winchester in the UK, as I've already mentioned. We've also got offices and laboratories in India and a new office in the United States. And as you can imagine, as within the consultancy arm of the business, we deal with everything you'd expect us to be able to deal with in preventing and dealing with fires and explosions. So all aspects of process safety management, industrial fire and explosion hazards, experts in electrostatics, and so on and so forth. And we also do a lot of bespoke training for companies on these topics. But as I say, we also have the luxury of having accredited laboratories that work under accredited quality management systems to be able to pull apart substances and determine their properties, either whether that's gas or vapor or powders, solids, electrostatic properties of materials, or even chemical reaction hazards, so calorimetry, DSC, differential scanning calorimetry, and all of these good things as well, all with an aim of trying to fully understand the properties of the substance, because everywhere in health and safety land we need to do this thing called a risk assessment to determine that what we're doing and what we're handling and how we're handling these materials, we want to do it safely. We don't want to have fires, we don't want to have explosions. They tend to potentially result in significant harm to humans, to the environment, and definitely to the business. Okay, and there's been lots of major incidents that have occurred with combustible solids. So what I want to do in the next sort of 40 minutes or so is just give you a few things to talk about and pass on some of my experience of dealing with dust explosibility testing information and how that's used in practice and why it's so important. So my primary focus, I will take you through the tests and the sorts of information that the tests give, but most importantly, how that test information is then taken within your processes to make them as safe as they can be. Okay. Now, as with any risk assessment, the first step in any risk assessment is the identification of the hazard. And in many respects, especially when we're dealing with liquids and gases, we're given a clue as to what the hazard is because it comes with hazard pictograms on the container. And I've just given the couple here for toxic substances and flammable substances. Okay, so if we're dealing with a flammable liquid like gasoline, for example, or acetone, on the container and on the material safety data sheet, it'll tell us how to handle that material properly, and it'll give us some of these flammability conditions and properties of the material. When we're dealing with combustible powders, very often that's not given. There is no pictograms that we stick on many powdered solids that could combust. Many of them are very common. Okay, so things that we use in our kitchens at home, flour, sugar, icing sugar, these sorts of materials will indeed combust and combust quite readily. Okay, but of course when we buy our bag of flour or icing sugar, it doesn't mention that it's a combustible solid. In an industrial situation, we'll have the material safety data sheet, but very often that doesn't give us much information at all, really. Often simply states that it may be capable of combustion, but doesn't give you any specific properties of that material. So it's a little bit difficult to use that information and to be able to prevent fires and explosions, what you have to do. Okay, and of course, as you'd expect, there's legislation on the topic. So the legislation in Europe and the similar legislation in the US and elsewhere around the world. We have the ATEX legislation in Europe and the UK. Okay, and essentially, if I boil what that legislation states down into three simple questions, it's avoid generating what's known as a flammable or explosive atmosphere, which is basically a mixture of a fuel and air, which is capable of combustion if it sees an ignition source. It's simply built around what's known as the fire triangle. So for combustion to occur, for something to burst into flame, we need a fuel, we need air or oxygen, and we need an ignition source. Okay, so very often, for example, for a flammable gas like natural gas, methane, when it's in the pipes, it's 100% methane, there's no air in there, it's not flammable, even though on the container it will state it's a flammable gas, an extremely flammable gas. In practice, it won't be. It can't ignite because there's insufficient air. Of course, if we have a leak from that system and release methane into the general atmosphere, it will then mix with air and will produce this flammable explosive atmosphere. So the first point is, can we avoid generating that flammable explosive atmosphere? And then the second tenet of the legislation is, if we can't avoid generating that flammable atmosphere, because after all our containment systems could leak, for example, then don't ignite it. Okay, so then a lot of the legislation then is focused on trying to prevent ignition sources by having ATEX certified electrical and mechanical equipment that shouldn't produce, that shouldn't give an effective ignition source if it's present within one of these flammable or explosive atmospheres. And then the third thing is, if it does ignite, because after all we're in probability land, we can do our best to prevent the generation of a flammable atmosphere. We can do our best to prevent an effective ignition source, but it could still happen. So if it does happen, then try and ensure that nobody's hurt by that ignition. So I talked earlier about the fire triangle. To turn that into an explosion, if we add into the fire triangle mixing, we get good mixing of the oxidant and the fuel, and we get some confinement that restricts the spread of the flame, then of course we can generate explosion over pressure. And you often hear this talked about as being the explosion pentagram. Okay, so mixing a fuel with air in the open, we can still have the mixing, but the confinement won't be there, so we'll end up with a flash fire. We won't end up with any explosion overpressure from that event. But if that occurs within a container, like a silo or a pipe, then pressure can be developed, and it then transitions into an explosion rather than simply a fire. Now let's go right back to basics now and just take you through just really what is a combustion reaction. It's nothing more than a chemical reaction. Okay, we are reacting a material with oxygen. So if that material is not fully oxidized, then in theory it's capable of combusting. It's capable of reacting with that oxygen and generate, and it'll be an exothermic reaction. So it will generate heat that could result in flames. And it's worth saying that really, on the whole, liquids and solids don't combust. It's the vapors and gases that combust. As we heat substances up, they can generate vapors. It's the vapors that will mix with the air and then undergo this chemical reaction. So combustion is just an oxidizing chemical reaction. That's all it is. And there's many substances out there in the food world, in the pharmaceutical world, where they may not be classified as flammable or combustible, but they will combust. And where solids are concerned, the reaction is no different, of course, but of course for this we then become a solid reaction. It's a surface reaction. That oxygen needs to react with the powder, with the solid, and it can only do that by starting off surface chemistry in the first place. And clearly, therefore, surface area to volume relationship is important. It's well known that if we have the larger the surface area, the easier it is to achieve a reaction, okay, and the quicker the reaction will occur. And that's the basis with powder combustibility. It's very dependent on the particle size distribution of that powder. Okay, so to determine whether or not a powder is combustible, there's a simple test known as the group A and B test, and you can see the apparatus here. So we put a small amount of the material on the base of this little machine. That blows a pulse of air through the substance that creates the flammable atmosphere, this a mixture of a dust cloud basically. And then you can see around the middle of the apparatus there's a couple of electrodes there that we stick a rather large electrostatic spark across those electrodes, and we see if it ignites. And if it does ignite, if we get a ball of flame coming out of the top of the equipment, as you can see in the picture, then it's a group A dust, it's combustible. And if it doesn't ignite, it's a group B dust, it's not combustible. Okay. Now, because of this surface area to volume relationship, the fineness of the powder, the dust, determine whether or not it's effectively going to be combustible. And generally speaking, we need to have powders fine enough that are less than 500 micron for them to be combustible. Now, many of the powders you will use may not be that fine, but they may have a fraction of material that's less than 500 micron. Okay, now in the test apparatus, we don't tend to test combustible solids as is. The standards, all the testing that I'm talking about is done according to specific standards, ISO, BSEN standards and the like, and they all call for the material to be sieved. So we will do the test on less than 500 micron. Even though in your processes, you know, the bulk material, the fraction of 500 micron dust is small. The question you then have to ask yourself is, well, can we separate out that dust within our processes? Because if the powder itself is a mixture of, you know, quite large particles with a little bit of dust, it's likely not to be combustible. Put it through this test as is, if you like, sample, it won't combust. And that's because there's insufficient dust for that reaction to go ahead. So the larger the particles, the more, you know, the less likely it is to result in this test proving positive and coming out as a group A. It is fair to say, in my experience, that we see many cases where powders are supplied with information from the suppliers that states it's not a combustible powder, but when it's put through this test, it actually does turn out to be combustible. And I can only assume it's because the suppliers have undertaken this test on the as-is material that they supply. The test hasn't been conducted correctly according to the standards, and we've sieved out the fine material. So that's lesson number one. In your actual process, that means, you know, if your process is dealing with powders and your processing operations aren't necessarily allowing that fine material to be raised into a dust cloud, then that's fine. But of course, there'll be many cases in your processes where attrition can occur. So the processing the material can break the material down into smaller particles. And in certain processing operations and your dust extraction systems and collection systems, where you're deliberately taking out this fine dusty material, within those unit operations, you are in fact generating the flammable cloud with very small particle size distribution material. For example, when we pulse the air to remove these fines from our filter bags, so to let them drop down into the collection chamber. Okay, so certain processes, especially if you're pneumatically conveying or things like that, or your dust collection systems, will be handling the fines. You'll be deliberately taking the fines out of your processing operation. So that simple test just tells us whether or not it's a combustible dust or not. And of course, if it's not combustible, everything's fine. You really don't need to build any precautions into it. Okay, because we're not going to be able to generate this flammable atmosphere. But if it is a combustible dust, if it's a group A dust, then of course we've got the third part of the fire triangle, the combustion triangle. Well, how much energy do I need to ignite that material? Okay, so a little example here, just to make what I've been talking about clear so far. If I take an iron bar, pure iron bar, we know that's not combustible. You know, we can melt it in furnaces and things, so we can then manipulate it and shape it and all the rest of the things that we can do. And if we heat it even up more, we'll end up with molten iron, but it won't burst into flame. Okay, it's not combustible. But if you remember going back to your school days in the chemistry laboratory, undoubtedly you will have picked up iron filings where we've grind down that metal bar and produce iron filings, and we've all tipped iron filings into a Bunsen burner flame, and we can see that we're starting to combust that material then. Okay? And if we grind that iron down even further and make it a very fine powder, it then basically turns into a spontaneously combustible or pyrophoric material. So as soon as it comes in contact with air, it will combust. Okay, so particle size distribution is important, but then we've got to have a sufficiently big ignition source if we've generated that flammable cloud. And if we look in the standards, in the ATEX directive standards, we'll find that they state that there are 13 potential ignition sources out there, many of which are quite common. The three I've got here are the most common ones. So heat or temperature. We know if we heat things up or raise the temperature, they can then tend to burst into flame. We know electrostatic sparks and mechanical sparks, friction sparks and things like that. But you know, electrostatic sparks is essentially just one form of electromagnetic radiation. All other electromagnetic radiations, whether that's laser, radio frequency, microwave or whatever, are capable of igniting dust clouds. Okay, so let's just have a look at a bit more of the test procedures on against these three most common ones. Okay, so the first test is the minimum ignition temperature test. So this is as defined as the lowest surface temperature that can ignite an optimum mixture of fuel and air. So what this is doing is, if you generate a flammable dust cloud and the only potential ignition source is temperature, what temperature would it ignite at? Okay, and that's the minimum ignition temperature. It's similar to the auto ignition temperature for gases and vapors. Okay, so again, we simply generate that flammable cloud by pulsing air through a sample of the powder, again done on fine material, less than 500 micron material, and we do that test at different temperatures. And when it does ignite and we get a ball of flame coming out the top of the apparatus, that is the minimum ignition temperature. So clearly, if you've got processing equipment on your site which is higher than that minimum ignition temperature, then it could be an effective ignition source. Conversely, if your temperatures of your equipment, your hot surfaces and things is lower than the minimum ignition temperature, you won't result in the combustion reaction or an explosion, okay, because you're operating below the minimum ignition temperature. Now that is ignition of the dust cloud. Solids themselves can ignite, and this is what's known as the layer ignition temperature, and we simply take a 5 millimeter deep layer of powder and we heat it up, and we see what temperature that the surface of that powder bursts into flame. Okay, so that's the layer ignition temperature. So this is important, because if you're not particularly good at keeping your powdered materials contained within your equipment, and you have losses of containment, you've got dust that settles out on the rafters of your piping systems in your factory and so on, or onto the electric motors and things, which can get hot, then you may end up with a fire because that layer self-combusts, because the temperature it's seeing is higher than the layer ignition temperature. Now these two test results result in what's known, we take the results of these two tests and we apply a safety factor to both these tests, and that sets what's known as the maximum permissible temperature that any of your equipment that is present within these flammable zones should should not exceed. Okay, and the simple safety factors as we take either we take 2/3 of the minimum ignition temperature value we've determined in the lab, or we take the 75 degrees off the layer ignition temperature, and we use the lowest of these two computations to set the maximum permissible temperature. So when if you've got electric motors present, then they will have a temperature classification generally, but what you're trying to do is to make sure that that motor or whatever cannot generate a temperature greater than the maximum permissible temperature created from this safety factor computation based upon the laboratory values of the minimum ignition temperature and the layer ignition temperature. These properties must be determined under laboratory conditions according to the standard methodologies. Okay, they are not capable of being calculated. It is not possible to calculate the minimum ignition temperature or the layer ignition temperature. So they've got to be measured in the laboratory. So temperature can be a source of effective ignition. Electrostatics can also be a source of effective ignition. And you can see this equipment is very similar to what we look at for the combustibility group A-B test. But what we're doing here, we can alter the size of the energy of the electrostatic spark that we put through the dust cloud. So this is determining the minimum ignition energy of a dust cloud. Okay, and we can also generate that electrostatic discharge in two ways. We can either generate it capacitively, or we can generate it in an induction manner. And essentially, when we use the capacitive methodology, it's giving us an indication of the minimum ignition energy from electrostatic ignition, from sparks generated due to electrostatic electricity. And then when we do it under induction methodology, it's effectively generating sparks of energy that you'd expect from mechanical sources, friction, and this sort of thing. Okay. Once we know the minimum ignition energy of a substance, of a dust cloud, that can determine then what we need to do to try and prevent that ignition. So if our minimum ignition energies are very low, we need to do more than if our minimum ignition energies are very large. The range of minimum ignition energies for substances can be very large, ranging from less than 1 millijoule up to thousands of millijoules. Generally speaking, ignition sources, whether they're electrostatic or mechanical, if the minimum ignition energy of the substance is greater than a joule or 1,000 millijoules, then that flammable cloud will not be ignited by electrostatic or mechanical means. If it's less than that, then it can be capable of ignition. So if the ignition source that we can generate is higher than the minimum ignition energy, then of course we need to take precautions. Just some typical minimum ignition values that I've taken from the literature, and be aware, as I've been talking about, taking values for substances from the literature is not considered good practice, because of course, as you can picture here, there's many different types of sugar, wheat flour, coal dust, wood flour, and so on. It's best to do it on the substances that you use rather than taking literature values. But it gives the point of, many active pharmaceutical ingredients have got very low minimum ignition energies. And very common things like wood dust and aluminium dust are not that high either. Yeah, so many of these materials don't require a lot of energy to cause ignition. Assessment of static hazards can be very complicated in a way, but what we're trying to do, to achieve ignition of a dust cloud, we need that flammable atmosphere, and movement of dust will generate charge. So pneumatic conveying of dust, mixing of dust in filling of silos and things will generate charge by virtue of flow. The electrostatic properties of the material itself, whether that's a conductive material or an insulating material, will determine whether or not that charge can be dissipated to earth or whether it can accumulate charge and keep hold of it for a long time. Okay, because if we've got charges accumulated, if there's a discharge mechanism, that's when we result in a spark occurring, and there's different types of spark that I'll take you through in a little while. But if we're generating charge, if we've got a flammable atmosphere there, if we can get a discharge and that discharge has got sufficient energy, it's greater than the minimum ignition energy, then it can, then we could end up with a fire or explosion. With electrostatics, there's a number of types of static discharges, and this is an increasing energy approach, really. So, well, not corona discharges tend not to ignite combustible dust. It's very low energy involved in a corona discharge. This is where you've got a sharp point where charge is accumulated at a sharp point, which is where the type of discharge comes from. We can have a spark discharge, a brush discharge. Brush discharges tend to produce around about 4 millijoules of energy, so relatively low. But we've also found through experience that even materials with minimum ignition energies less than 4 millijoules will not be ignited by a brush discharge. Okay, we can have what's called a propagating brush discharge, and this sort of discharge is associated with thin insulating. So, for example, if I've got 2 sheets of acetate film like we used to have before we had laptop projectors and things, and we used to give presentations on acetate sheets, separating those 2 sheets from apart can result in a propagating brush discharge. And propagating brush discharges can have energies measured in joules, so a large source of ignition there. Okay, so different means of static discharges, different ways of preventing electrostatic discharges, and they're all there in the standards, the applicable ATEX standards, to help you determine how to prevent these types of discharge. But you need to know it because this gives you need to know what type of discharge you could potentially have and put that in relation to the minimum ignition energy. If it's larger, if the discharge energy can be larger than the minimum ignition energy, it's likely to result in potential problems and ignitions. So we've done our best to try and prevent ignition of a flammable cloud. In terms of eliminating or preventing the flammable atmosphere, things that I'm not talking about today, but this is where you'd use inerting, or you'd work under vacuum, or you reduce the level of oxygen or air present in the atmosphere. Okay, that can avoid the generation of a flammable atmosphere, and avoiding electrostatic and mechanical ignition sources can be achieved by good earthing and various other techniques, which I'm not going to go into in any great detail today, because it'd spend at least another 2 hours going through those sorts of things. But we've done our best to prevent. But that third step I mentioned was, if an ignition source does occur within a flammable atmosphere, then what actually happens if it's ignited? Well, obviously, we result in generation of flame, and because we've got a combustion reaction, and we've got the potential, if it's confined, for rapid development of pressure. Okay, so if you picture it on your processes, if an ignition occurs within some of your processing equipment, within your dust collector, within some of your pneumatic transfers, within your mixing systems, okay, then you'll generate flame and you'll generate pressure. And of course, if the pressure's too high, higher than what the containment system can contain, you'll start blowing the equipment apart and generating missiles and such and so forth. So, armed with this knowledge, we can then design precautionary equipment to install on our equipment to deal with this generation of flame and rapid development of pressure, to stop the machine, but to stop the equipment from being blown apart. And the test that's done to generate this sort of information is known as the 20-litre sphere explosion severity equipment. You can see a picture of it here. Okay, so what this, again, it's very similar to the rest. We put a sample in, we generate the dust cloud, and we put an ignition source through it. But this is a very high integrity pressure system, and we can measure the pressure. So we can measure the maximum pressure that that ignited event will generate. And we could be talking in excess of about 12 bars. Okay, so a significant pressure. It will also measure the rate of pressure rise, the dP by dt, how quickly that pressure is generated. And once we know that value, we can then look up and look at the range of that value and determine what's known as the dust constant. So we can have a what's known as an ST1, an ST2, or an ST3 dust. And the higher the number, the greater the maximum rate of pressure rise. The more vicious the explosion is, the more rapidly it occurs. So things like metal dusts and certain active pharmaceutical ingredients can be ST3 dusts. Many foodstuffs are ST1 dusts. They'll still explode, they're just not as vicious. Maximum explosion pressures are reduced, and the rate of pressure rise is reduced also. Once we have this data, we can then use that data to stop blowing bits of metal around our plants. It's what's known as the basis of safety. We can design things to deal with that ignited event. And it's generally three approaches that we take. We either contain the explosion over pressure. So the containment system, the mixer, the ductwork or whatever is built so robustly that it can withstand that rate of pressure rise and maximum pressure. And there's two types of containment equipment there. One that will contain it with no deformation, and one that will contain it, so the effects of the flame and the explosion pressure won't be outside of the containment system, but it will deform the equipment. So in the former, where it's not deformed, of course you can clean it out and start your equipment up again. If it deforms, then of course it's weakened, so essentially means that that equipment needs to be replaced. Okay, but it's building that containment system to withstand the pressure and the temperature that could occur from using that test data. Another way of doing it is suppression. So what this says is it detects the flame or the pressure, and then it does something about it to suppress that rate of pressure rise or that maximum pressure. So that it can happen in various ways. It can occur, you can fire off very rapidly some extinguishant, maybe water, maybe CO2 or something else, into that containment system, which kills the combustion reaction. Okay. Both of these techniques, in fact, all of these techniques require good isolation. So you've got to remember that I'm generating flame, I'm generating pressure. Just like water, it will take the path of least resistance. So if there are openings within your containment systems, which there will be, because obviously you're feeding material into something and you're feeding material out of something, if that flame can progress along those ductwork and what have you, and then go into another piece of equipment containing combustible material, then we're not isolating that explosion to where it's occurred. And this has happened on many, many occasions, on many large dust explosions, where essentially the whole factory has gone up because we've not been able to isolate the effects of flame or pressure transversing from one piece of equipment to another. The most common means of dealing with an ignited event is venting. We have a weak point on the containment vessel which opens and allows the flame and the explosion pressure to be released from the containment, the mixer, the ductwork or whatever, into a safe location. Okay, and this is the most common way of dealing with an ignited event. Many of your dust collection systems, if they're collecting combustible powders, will have an explosion relief panel on them. Okay. Obviously, for venting to be effective, the vent needs to open at a very low pressure. The vent needs to have an area that's large enough to reduce the pressure in the containment system below any damaging pressure that could happen to the equipment. Okay, so explosion relief panels need to have a low inertia, a small inertia. They need to be very light and get out of the way quickly to allow you to allow that area of venting to be calculated. It's the explosion severity data, your rate of pressure rise, and your maximum pressure that is used in the calculations to determine what vent area that you need. Okay, and also what pressure it should open at. Obviously, needs to be lower than what the pressure rating of your equipment is, if there is a pressure rating. Many dust explosion collection systems are simply made of angle iron and sheet metal. They don't withstand much pressure at all. Okay, but it needs to be designed correctly. And boy, can I tell you the number of times when I see venting that is clearly inappropriate. Venting that I've seen explosion relief vents that weigh 2 tons apiece because they've been designed by construction engineers, located outdoors. They've been designed by construction engineers to withstand snow loading and wind loading and things like this. I've seen them used as walkways that you can walk across. Now, clearly, shifting 2 tons of metal quickly, it won't happen quickly. Yeah. So the back pressure that remains within your containment system remains relatively high. shifting 2 tons of metal requires a fair bit of pressure, and we need to move that vent quickly. Okay, I've seen vents positioned on the clean side of a dust collection system. So that on the clean side, the output from the filters, if you like, it should be clean air. These are not explosion vents, even explosion relief vents, even though the supplier of your dust collection system has told you it's an explosion relief valve. That is simply an air intake. I've seen explosion relief panels on large dust collector systems where the dirty volume is around 10 cubic meters, and they've got one explosion relief panel measuring 0.5 meter by 0.5 meter, and it's held on by toggle clamps. Okay, so that is an inspection hatch. It is not an effective explosion relief panel. It is nowhere near the area that is required, and it won't move quickly because toggle switches will need to break before that panel would be released. Okay, so you've got to be very careful that when you do source somebody to manufacture or supply you with a dust explosion unit, that they understand what's needed, and you know that what they've provided is acceptable or not. Okay, this is very important, and I see it time and time again. Practically every site I go to do ATEX assessments on, and I ask them, can you give me the evidence that that explosion vent is sized appropriately? Companies do not have that data. They may have once had that data, but it was done 30 years ago. Yeah, they've got no evidence now to say that what pressure that vent will open at, whether the size is adequate, whether it's based upon the correct substance, the substance that's now used, and everything else. So you've got to be extremely careful when designing these things. It's got to be based upon the explosion data. If you're asking your supplier of dust collection system and they don't ask you for that information, they don't say to you, what is the substance, what is the P max, what is the dP by dt, what is the ST value of your particular dust, they will not be able to design that system appropriately. So I've ended a bit on a downer there. Yeah, but you know, these are the things that we see in practice when we are looking at systems that are out there in the real world designed to keep us safe. Yeah, it's important to state that when we're talking with powders, many of these properties are not calculable. They need to be measured in laboratory conditions under specified methodologies. Okay, there's many ways of stopping these fires and explosions. As I've said before, prevent the formation of the flammable atmosphere. Within equipment, that's generally done by either working under vacuum or working under nitrogen atmospheres or inert atmospheres, this sort of thing, limiting the oxygen concentration. Prevention of ignition to try and stop the ignition occurring. And as I say, that in itself is a whole topic on its own, which undoubtedly we will do a webinar in the near future on electrostatics. We did one relatively recently. But also designing your systems to be able to deal with the ignited events. So hopefully there's been something that I've said today that's spark some interest, spark some things in your mind that we better go out and check. Do we have this data? How do we know that our systems that we've got are effectively designed, are fit for purpose? Of course, if you need any help on that, if you need any of your substances testing, Sigma-HSE is the people to come to. We can help you in your process design. We can help you determine the properties of your materials. With that, I'd like to thank you very much for listening. If you'd like to contact us, just send us an email in to info@sigma-hse.com, or give us a call on that number and somebody would be quite happy to talk to you. But on that, I'd like to say thank you very much for listening. Hope you found it interesting, and have a good weekend, and bye bye.